Hi everyone, this is Chuheng, Tan, and Haipeng. And our project is called RE-MYCE. It's about landslide responsive design in Yunnan Mountains regions. Our study expanding from the land use and urban infrastructure development to the mycelium biocomposite structure design. The landslide is a nature disaster which is high speed, high energy, and extremely destructive. It's usually caused by the natures and human activities like the mountains movements, unstable weather, mining and blasting, and urbanizations. And this disaster can cause a great damage to the slopes and buildings, leading to the significant lives and economic loss. Our story starting from the Yunnan province, China, the topography is ranging from the world's steepest valleys to the highest peaks in the Himalayas. In the last 5 decades, the unstable weather increasing the disaster like the droughts and floods. This site is a landslide-affected village in the suburbs of Malung district, 5 kilometers away from the city centers, and the population is nearly 5,000 residents. And over the past 20 years, the landslide has led to the constant agricultural and building damage, affecting more than 8,000 people in the cities. So when we're looking into the vernacular buildings in Yunnan, there are mainly 4 types of traditional buildings. The layout is often symmetrical and formal, with the courtyard located in the center and around with the master rooms and the side rooms. And this is a building features the timber structure, which can transfer the loads and distribute the weight throughout the buildings. And this is the local living scenes in Yunnan, and timbers and bamboo are the main material for the buildings. And the elevated bottom is for the ventilations and mitigating the water flow impact. So for the first step of the urban planning, we take the reference of the local annual rainfalls, evaporation rates, and the water erosion data to predict the extremely landslide conditions. Then we generate a risky map and summarize the context information like the populations, incomes, crops, and areas of farmlands and housings. And then include the government's rural development requirements and their future plannings, and it will provide the guidance for our design development. Then we move to the landslide responsive land use and the urban infrastructure development. So firstly, in terms of the building tissue evaluation, although we have a landslide simulation and risky area zoning, it also needs other factors to control the land use. The first one is the slope elevations, which will influence the construction locations. And the second one is the slope angle, which will determine the buildings and planning locations. And the third one is the slope orientations. It determines how much area can be exposed to the sunlight and wind. And the next is the landslide sediments, which show the soil fertility levels and determine the areas and location of the agricultural field. And the last one is the soil erosion. Evaluate whether the construction is appropriated. Then we overlap these 5 maps together and generate a new map called the land use adaptation level map, which divides the whole site into 5 levels from the most suitable to the most unsuitable. And the distance to the current village center will define the land use functions. Note that here the adaptation level is a priority of the agricultural constructions. So the weightage of each maps are defined as gene domains, and in our initial findings show the sediments and the soil erosion have the priority in affecting the land's adaptability and the slow safety. So we need to remapping the gene into a new gene domain and keep this influence balance. For optimizations, we carry forward the MSC phases data on the future village construction needs, aiming to closely match the area requirements for each functions. So this is the optimization process of the land use adaptation evaluation. So finally, we choose the average finished objective individual as our final selection in this step. So once the land use planning is established, we will focus on the setting up the slope infrastructures, which involve the slope modification, drainage system, retaining structure, and the building placements. For the slope modification, the 2 main principles are excavation and filling the matters. No matter what kinds of a method we use, the goal is to increase the numbers of steps and reduce the slope angles. And the drainage setup, including the stepping channels in high-risk slopes and the surface and drains for medium risky slopes. And this is a case study of a drainage system in Australia. And about the retaining structure, it contains the gravities, gripworks, buttress, coffers, and the pipers. It also shows the bioengineering with the plant's roots can prevent the slides, overturns, and failures. Also, the planting vegetation on slopes is an effective way for the ecological protections. The vertical slopes suit the climbers, while the gentle angles can support the grass, ferns, shrubs, and trees. The stepping terrace is a famous agricultural practice in Yunnan. Also plays a role in soil erosion controls and conservation, especially on the slope between 3 to 35 degrees. For the building setup, we should make the structure as regular and compact as possible. So this section sketch shows the cohesive design vision that merge our slope management with the building forms, vernacular elements, and the timber structure. So moving back on our project, it's time to apply the above research to our urban infrastructure development. So our site is setting on the original village that covers the median suitable area, less suitable, and the unsuitable area. When designing the building morphology, we want to incorporate the traditional feature like the courtyard and interlocking layouts and ensuring the proper spacing between each buildings. So based on the basal laws, the flows can lose energy when distributed to the wider region. This experiment shows in a single area's layout, the energy travels in a straight lines and collide with each other in a chain reaction. But if the blocks interlock too closely, it should also trigger a domino effect. But when allowing the spacing after interlocking, there's room for the energy to dissipate, and you can limit the excessive movement when maintaining the interlocking. So we need to define the gene domain of how much distance can both dissipate the energy and maintaining the interlocking. So at the distance below the 1 meter, you will collide, and above 3 meters, we will have a no interlocking constraints effect. Now we can set up our building morphology and cluster layout parameter to optimization in each area. And this is the building parameter in the less suitable area, unsuitable area, and in moderate suitable area. And also we combine the slope treatment and go and slope and gene parameters. And also connect the drainage system designs as a group of a parameter. And also we should ensure a certain public space for daily living and emergency shelter. So the ratio of residents and public is also a group of a parameter. And we add the stepping terrace following the local agricultural products and located in the high-risk area. So that will be a very huge and comprehensive optimization that can integrate all the infrastructure system for the whole village. So to simplify the computing, we set up 3 groups of a compounds equation as objective for slope, drainage, and building. The first one is to increase the slope factors and minimize the earthwork balance volumes. And the second one is to maximize the drainage water capacity and minimize the pipes construction volumes. And the third one is ensure the ratios of residential and public space can meet the local needs. And this is the urban infrastructure optimization process for the whole village. And after that, we choose 6 individuals to validate their landslide residence capacity and select the safety one for the further structure design. In this slope area, we can see in anticipated soil erosion. So the next steps, the structure strategy should focus on the slope stability and the crack prevention. And in the valley area, the sediment accumulated. We want to make the best use of the farming.
After complicating the land use arrangement and the development of the infrastructures, we then focus on the structural systems. After this phase involves understanding the principle of landslide resistant structures. It also contains the selection of appropriate material and the establishment of protective structure principle with rigid protection and flexible protection. When we move to choose the material as flexible cushions, we find that mycelium composite is biodegradable material that are known for their high-quality lightweight and cushioning properties. We select sugarcane, a common crop in Yunnan, as it shows promising results in terms of diameter and strength. This is our substrate treatment process. It took about 10 days for our material samples that are ready to be baked. The production is called mycelium composite. For protective facade systems, we are inspired by the sandwich panel that are composed of 2 timber panel and a mycelium composite core. These have an excellent cushioning capacity, but they have limitations due to their low strength and brittleness. So this sandwich structure can improve the bending and compression of both timber and mycelium composite. For protecting the main structure, it can provide cushioning as outer layer for the column and in the core. We created timber mold for mycelium composite brick, conducting physical tests by stacking 2.0 kilogram brick until they are all used up or the material fails. They are the physical experiment of compression and shear force comparing timber mycelium and timber mycelium sandwich brick with data above. The figure data show that while all 3 materials excel in compression, mycelium underperform in shear strength compared to timber and sandwich brick, with timber displaying greater displacement and under shear force than sandwich brick. As landside impacts on material cannot be physically tested, we ran digital simulation for a single plank, a double plank, and a sandwich structure, using specific data and formula in the simulation process. Next are the structural systems, which are rigidity and flexible protection. The bracket structure on the column in monocular building reveal their structure are highly resistant to earthquake and impact. They results show topological optimization for structural simplification and enhancement, which cut material usages but keep stability intact. In designing rigid protection, we apply topologic optimization and rationalize them to enhance the structural strength. After defining the beam column system, we strengthen the connection of the column to the roots and the ground by topologic optimization for both reduce the material use and ensure the definiteness. Then we rationalize the results based on the topologic optimization. The outer part we use mycelium biocomposite as a cushion, and the inner part as rigid supportive structures. For flexible protection, we conduct a finite element analysis to create a deflection map on the facade. This helps identify areas with higher deflection, where we then reinforce with thinner wall to ensure stability. This step is finite element analysis. And based on the finite element analysis, the larger the displacement, the more the facade bulge out. Finally, we place the sandwich panel according to the distance between original and the bulge out surface. Before running the optimization, we need to define the column and beam size range as joint domain. So here, we perform a rigid body dynamic on the rigid structures. We found that if the width of the beam and column is smaller than 200 millimeters, the structure will destroy totally. If above 600, the structure will not have any change. So 200 to 600 are our optimized domain. Also for the flexible sandwich dimension, we find that if the panel width is smaller than 0.4 meter, it will be destroyed totally. If bigger than 1.4 meter, it will not have any change. When the panel width is less than 1 meter, it will be more affected by mud flow. But when it is larger than 1 meter, it will be more affected by water flow. After the size range is determined, we set up evolutionary optimization to optimize the size of our component to get the result with the minimum amount of the material and the displacement. It shows optimization solutions. Now we extract the percentage in the individual evaluate and compare the performance under the mud flow. When choose the best parameter to drive paradigm to fit the building construction, but after a series of optimization, they are good enough so that the simulation results are all similar. We will choose the less material usages as our final paradigm. This part is for building assemble, but before install the building structure, it needs to insert the epoxy pipe into the soil. It not only improves the soil stability, when the epoxy pipe combines the column, it also enhances the building stability. After the epoxy pipe and the column, it can be assembled the slab, beam, and then optimize the structures. Finally, install the mycelium fence. This part is for column details. The epoxy pipe not only improve the soil strength, but also provide nutrients for mycelium. And the roots of the mushroom also enhance the stability between the pile and soil. And the detail and assembling method of the sandwich panel, it contains 3 parts: joinery, frame, and the sandwich panel. This is the physical model.
So finally, we are starting the life cycle growing of the village to reveal the whole design paradigm. We first get the ready-made terrains. It contains the stepped terrace, drainage channels, and the retaining structure. Then the public space, and get the risky map of a landslide risky. An initial framework setup, and assembling the facade, and the final view of the whole village. So looking at the life cycle vision, we create a blueprint of the construction of this village. So after the landslide, the slope terrains will slow down the mud flow speed and acknowledge some erosions. Then the housing are raising on this landscape. And the mycelium biocomposite will act as a columns and foundation protection, shape the fence, and also it will become the sandwich panel for facade systems. And the mycelium fence at the bottom will integrate the nailing structure and foundation to create the bioslope protections. Also, it will act as a water-retaining fertilizers that allows the planting to grow. So finally, in our visions, the building are not only the building itself that will harm the nature, but it will serve as a fertilizer station for the ecology prevention and will expanding to the whole village. So this is a section of the village which integrate all the infrastructure we have mentioned about system and the nature. And we hope this pattern will become a new paradigms that will benefit the planning and construction for the village and under the landslide affected in the mountain areas. So thank you.
I'll go first then. You mentioned in your presentation something like mycelium cushioning. Can you explain that?
Mycelium cushioning is like using the mycelium biocomposite as can replace by the foams and EPS material that cannot be recycled.
So isn't it cushioning against what? Against the landslide or?
Sorry, we can explain more. It cannot resisting as we can resisting the whole landslide, but it can partly to mitigating the impact.
Okay, all right.
Yeah.
I'm kind of in 2 ways about your presentation. Beautiful presentation, by the way. Your first part was beautifully rational and using all the tools and techniques that you've been taught in a very pragmatic manner, like identify where landslides would be. It was actually beautifully done, I thought. And I thought what I really liked about it is that you didn't feel the need to completely invent a new topology or something like that for this area. You kept quite in tone with the buildings that are there, right? I just have a bit of an issue with the second part, and that was the mycelium cushioning comes in. You have these analyses that kind of shows how, certain structures will be able to kind of withstand these landslides. I'm not sure, I see these landslides and I think you're kind of doomed anyway if you see what these things do. I don't think these buildings could actually withstand much anything. I think if you have to build something that withstands these landslides, Jesus, you're going to have to do a lot more. I'm not a structural engineer, so I'm going to leave it up to you to comment on that. So I'm kind of, it's this kind of mixture, this presentation between a very believable, very rational, pragmatic proposal, which I really like, and then the last bit, I'm a little bit like, I don't believe it. Even if you have the analysis and the simulations done. Right, so that's kind of where I am with this project. But I think it's a beautiful intervention though, and I love the fact that you use mycelium. We've tried it ourselves. Well done.
So I can explain a little bit.
Go for it.
So in the first part, So thank you for your comments. And I think the building itself cannot resisting all the impact itself. It's the last line we can survive at the last. So the most important part in the urban infrastructure development, like this, how we can develop the slope angles and to reduce the mud flow step by step, and we insert the stepping terrace which can hold the soil erosion together, and that will be the best part to control the soil erosion. And so when we're considering the facade system and what kinds of material we can use, we are thinking about to use the local material that Yunnan is a very famous material in Yunnan. And we are thinking about using this material in this replacement and recycle building, and that will be a best solution for that. Yeah.
Okay, very good answer. Thank you.
Thank you.
Yeah, thanks a lot. I think echo the comments. It's a very beautiful presentation, and thanks for showing such a nice part of the world to us in the first images. I mean, just again, echoing the comment, it's very nice, the research you have done. Also, you went quite into the technical side of it. I just got one doubt on the optimization that you done at the very beginning, because you said you took all the different conditions of the slope sort of analysis and the orientation and all of that, and then you sort of went to the optimizer and you took the median results. But that's what I'm thinking. Surely the median and average way is not the right answer for this, as you probably are looking to take the best case scenario for all the parts. So in terms of optimization, I'm not quite sure. The second part, but it's really the right approach though, in terms of, if you get the numbers right. And the second part I think you've done, you proposed the terracing, which is very, very interesting from the original terrain. And I wonder if that operation, based on your research, wouldn't have already have enabled you to remove the risk of landslide in some areas to allow you to develop then your housing. Because I mean, there's a lot of geotechnical work you're proposing to do there, and in doing that, you already, enhancing the terrain. So I think that's sort of the part that I'm not quite sure about the trajectory. But other than that, I think it's just very interesting, and I did like as well the fact that you kind of stayed close to the original architecture, which was quite nice.
Yeah, thank you guys. This was a really nice presentation and really good process and very solid. I have like two comments. There's one part of the presentation that I'm really taken by, which is the moment where you're studying the porosity of the four parts, like the interlocking, the separation, and you are really calibrating something at the scale of the volume, no? And then you mentioned the courtyard type, and you say that in this village, it seems that it operates always in courtyard conditions. And now I see this image and I wonder, where are the courtyards? And maybe if that could have been the driving force to design in relationship to this reinforcement of the landscape, the main part that around which the secondary units will aggregate, public and private even. I think there is a project as an underground thread of the project, which is this kind of property possibility. You spoke about property value or land value at the very beginning, no? And I'm going to the very beginning because I think there were some nice ideas that if they come back here and you're building, not rebuilding a village, it seems like too ambitious, no? Like you're envisioning a system that reinforces the land so that you can build in this situation, and then you might provide the idea of courtyard. Maybe you could open the idea of courtyard, because there is a potential there, not only for the house, but also as a public space and so on. I think you know where I'm getting. So if I were to see this here, you would be enhancing that possibility. And that is also why when we see the partition system, I also struggle a bit, because I see that there is an investigation on it, which is like very thorough and seems very relevant. But I wonder, what is the role of this partition system? Because the partition is not for rigidifying, because it's the piloting system what makes this system that is so much based on points. The fact that it's based on points and not lines is what makes it sturdy enough, so on, like resilient to the landslide, so on. So when you turned everything into points, which is very smart, then you introduce planes. And these planes are to segregate space. and then you go into another kind of realm. So that's where I think we are struggling to understand, because it's not a structural operation per se, and then you test it against the water itself, but you are speaking about landslide. So the water is in the equation, but more like as a mediated by the land, right? So I think maybe that part, that's why we don't fully get it. What is the role of testing this against the water? I'm still not sure. Like, it might operate well and it performs great, and you patent it, and that's amazing. But I'm not sure I understand here what it gives back to the first part, because when you showed us the typology, you showed us the structure system and you valued it, but you didn't speak about partitions or envelope. So it seems that there is, to me, something like a gap that you can easily fill. But anyway, I'm very interested in the project, and that's why I'm kind of sitting in the middle of your thinking. But these are the two aspects that I would say I would have inquired a bit further. Thank you.
Yes.